So let's do a simple example. Let's look at methane, which is the molecule CH4. The Lewis dot structure for methane has a carbon in the middle of the molecule, and it is attached to 4 separate hydrogens. So our number of attached atoms equals 4, and the number of lone pairs equals 0. So again, when we think of hybridization about an atom like carbon, it has an S and 3 P's as our available orbital set to construct our hybrids. And we saw in an earlier video that the minimum number of hybrids that we're going to need is going to be equal to the number of attached atoms. Well, we have 4 attached atoms. We have 4 available atomic orbitals. We need to mix all these together to make 4 hybrid, because we need 4 hybrid orbitals. To get 4 hybrid orbitals out, we need to mix all 4 of our starting atomic orbitals together. So this is going to give us 4 sp3 hybrids. We're going to have 0 unhybridized p's left over. That's fine. We don't need them. So what do we learn when we determine a hybridization? Can we just determine the hybridization is going to be sp3 hybridization? Well, one thing hybridization tells us is the bond angle. So sp3 hybrids all have a bond angle of approximately 109. As it turns out, methane is not just approximately 109, it's 109.5 exactly. Okay, great. So all sp3 hybridized atoms, whether it's methane or something else, they're going to have a bond angle that's really close to this 109 value. Not exactly, but that's a great number to throw out there every time. So we can learn the bond angle. We can also learn the geometry. Now, geometry is not simply determined by hybridization, but it's also connected to the number of attached atoms. So geometry is a function of 2 things. One, it's our hybridization, as well as the number of bonded atoms. When you have 4 bonded atoms and sp hybridization, you have a tetrahedral geometry. So what I'm saying is when people say something's sp3 hybridized, don't say, oh, it's sp3 hybridized, it must be tetrahedral. That's not true. It's only tetrahedral if you have 4 atoms bonded to the central atom. So let's look at what methane, how it appears structurally. We have a carbon in the middle, and we're going to have all 4 of our hydrogens surrounding this carbon equally spaced about the carbon in 3 dimensions. So to show this, we're going to show 2 of these hydrogens with regular bonds, and this bond angle, we're trying to represent this and sort of act like this is about 109, 109.5. I've really done it about 120. It's easier to draw a 120 than a 109, so I tend to draw these as 120. So these 2 bonds are normal. That means they're supposed to show these carbon-hydrogen bonds are within the plane of the writing surface. The other 2 bonds are going to be oriented out of the plane. One's going to be above the plane, and we'll draw this what we call wedged. The wedged atom is coming up out of the plane, so this hydrogen is kind of poking up above the plane of the writing surface. And the other one I'm going to draw is a hashed bond. That's not a dotted line. That's not a dashed line. It's called hashed because these things are oriented and have this orientation. It's a hashed line, and that hydrogen is actually below the plane of the writing surface. And notice that the 2 atoms that are above and below the writing surface, they're kind of drawn close together. This is a tetrahedral, how you properly show a tetrahedral center. This is a tetrahedral sp3 hybridized methane atom.